We've all been tracking the explosion of AI agents, these systems that use LLMs to plan, to act, and solve some really complex tasks. But the sources you brought today show the whole field is hitting, well, a pretty massive conceptual wall.
That's right. And that next evolution, moving agents from being these static tools to systems that are constantly adapting, that's officially underway.
So what's the core problem they're pointing to?
The core critique really is that most AI agent systems today, whether it's a single chatbot or, a whole team of them, are fundamentally static.
Meaning their rules, their configurations,
Yes.
they're all manually built and then just fixed at deployment.
Exactly. And that brittleness, as you called it, is a huge issue in the real world.
So how does that actually play out? I mean, what happens when a static agent meets a dynamic problem?
Well, they tend to fail, sometimes spectacularly. If an API suddenly changes or a user's goal shifts halfway through a long conversation, the agent just really ends. It doesn't have the tools to self-diagnose and rewire its own insides.
It can't adapt.
It can't. It lacks that continuous adaptability for what the researchers are starting to call lifelong agentic systems.
Okay, so that's our mission for this deep dive then, to really get into the mechanics of this jump, to understand how these agents can achieve continuous self-improvement, optimizing themselves using feedback from their environment.
Precisely. And the technical definition we're working with here is pretty specific. A self-evolving AI agent is an autonomous system that continuously and systematically optimizes its internal parts by interacting with its environment.
All to adapt to new tasks while, and this is key, preserving safety and boosting performance.
It's so much more than just training a better model. This is about teaching the AI to constantly remodel itself.
Right, and the research seems to track this almost like a historical timeline, right? Moving from these fixed models to something totally autonomous.
Yeah, it's a really clear progression. It all starts with MOP, which is Model Offline Pre-training.
Okay, so that's the foundation. Training the base model on a huge static data set, a snapshot in time.
A snapshot in time, exactly. Then the next phase is MOA, or Model Online Adaptation.
And this is where we start to see some of those post-deployment tweaks, like a little bit of fine-tuning or maybe RLHF, using human feedback to kind of nudge the model.
It's an external guiding hand. But then came MAO, Multi-Agent Orchestration.
This is where you see multiple agents collaborating, right? Exchanging messages, maybe debating a problem.
Yes, but, and this is the critical distinction, while they're talking to each other, the underlying code, the parameters of each individual agent, they stay fixed. It's all collaboration without any self-modification.
Which brings us to the destination, AE, multi-agent self-evolving.
Exactly. AEs is that lifelong continuous loop. It's where the agents are refining everything, their prompts, their memory, how they use tools, even how they talk to each other.
All based on environmental feedback and what the papers call meta-rewards.
Right. And since you've got these agents constantly changing their own behavior, the researchers knew they had to set up some guardrails.
So this is where the Asimov-inspired laws come in. 3 principles, and I hear they're strictly hierarchical.
They are. The first law is endure, or safety adaptation. It just means the agent has to maintain safety and stability during any change it makes to itself.
So rule number 1, don't break yourself.
Pretty much. That's the non-negotiable floor. Then the second law is excel, or performance preservation.
Okay, so subject to not breaking anything.
Right. Subject to the first law, the agent has to make sure its changes either improve its performance or, at the very least, don't make it worse. It has to measure the outcome.
And the engine that actually pushes for all this change.
That's the third law. Evolve, or autonomous evolution. Subject to the first 2, the agent must autonomously optimize itself in response to a changing world. It's a framework that balances that drive to evolve with safety and performance.
Okay, so those are the guardrails. Now, how do you actually build the machinery for this? Let's get into the conceptual framework that makes this whole loop work.
I think the easiest way to think about it is like a startup that's constantly trying to find product market fit. There are 4 main parts.
I like that analogy. Let's map it out.
So first, you have the system inputs. This is the task, the goal, the data. In our analogy, that's the original business plan.
Okay, and second is the agent system, A. That's the thing you're trying to optimize. The LLM, the prompts, the memory, the tools.
Right. In our startup, the agent system is the team. Your engineers, your product designers, your sales staff.
And then third, you've got the environment. This is what provides the feedback. For a coding agent, maybe that's a compiler telling it if the code runs.
Exactly. The environment is the market. It's giving you sales figures, user reviews, crash reports. It's generating all that feedback.
Which brings us to the last piece, The optimizers. This is the intelligence driving the change.
The optimizers are like the board of directors or the R&D team. They take the market feedback and use it to refine the agent system, the team.
So they define what can be changed, the search space, like the org chart, and how to change it, the optimization algorithm.
Precisely. And the whole goal is to find the best version of that team or agent that maximizes positive feedback from the market, all while staying inside the guardrails of those three laws.
It's a closed, iterative loop, always pushing for improvement. So let's zoom in on a single agent, because you mentioned that's where a lot of the action is right now.
It is. I mean, constantly retraining the entire LLM backbone is just too expensive. So the first real battleground for evolution is everything around the model.
Its instructions, its memory, its tools. Let's start with prompt optimization. We all know how sensitive LLMs are to tiny changes in phrasing.
And we're seeing some really creative approaches here. The first couple are what you'd expect. Edit-based, where you just make small tweaks to a prompt, and generative, where the LLM writes whole new prompts from scratch.
But the one that really jumped out at me was text gradient-based methods. That sounds like you're using natural language to do math.
That's a great way to put it. Instead of using mathematical derivatives, these systems get an LLM to generate natural language criticism, a text gradient, that tells the agent exactly how to fix its prompt.
So the system can fail a task and literally say to itself, I failed because my instructions in step 3 were too vague about the file path. I need to be more specific.
Yes, that's automatic textual criticism. And then you have the really wild stuff, like evolutionary optimization.
This is prompt breeder.
Right. It treats prompts like a biological population. It uses what it calls mutation prompts, which are instructions on how to change other prompts to evolve the whole set over generations.
That is wild, applying biology to code instructions. Okay, so after instructions, the next thing to evolve is memory optimization. This is huge for getting past context window limits.
For sure. And a lot of the focus is on what happens at inference time. For short-term memory, it's about managing that immediate context. We see things like recursive summarization, but also systems like reflection.
And reflection is interesting because it stores insights from past failures, right? It's specifically for self-improvement.
It's a memory of what not to do. And then for the bigger stuff, you have long-term memory, usually powered by RAG retrieval augmented generation.
But it's not just a simple vector search anymore, is it? Tell us about HippoRAG.
HippoRAG is inspired by the human hippocampus. So instead of just throwing text into a big searchable database, it uses lightweight knowledge graphs to index information.
So it captures the relationships between pieces of information.
Exactly. So it doesn't just retrieve the word apple. It knows that this apple was discussed in the context of Steve Jobs 2 months ago, which is relevant to your current question about corporate founders.
It understands contextual dependency over time. That's a big step up.
It makes retrieval much smarter and helps the agent avoid that context drift you see in long conversations.
So the agent has better instructions and a better memory. Now it needs to evolve its ability to act. That brings us to tool optimization, giving the agent better hands.
Right. And there are kind of 3 levels to this. First is training-based, where you fine-tune the model on examples of good tool use, like what they did with ToolLM.
Okay, learning by example.
Then there's inference time optimization, which is about making better choices in the moment. This could be simplifying the tool's documentation on the fly, like EasyTool does.
Or using more advanced search methods to pick the right tool for the job.
Right, like the toolchain systems that calculate the potential cost of using different APIs before they even make a call.
But the real game changer is that third level, tool functionality optimization. This is where the agent doesn't just use tools, it creates them.
That's the leap. Systems like Creator can literally generate new tool documentation and the executable code for that tool when they face a problem they can't solve. The agent designs a new function, writes the code, and adds it to its own toolkit.
Wow, okay. That transition from just using tools to creating them feels like a direct bridge to multi-agent systems. If one agent can do this, what happens when a whole team starts evolving?
Well, multi-agent systems are already attractive for a bunch of reasons. Specialization, robustness, but they have that same static problem. Most of them use a fixed, manually designed workflow.
And a fixed workflow isn't always optimal. If the goal changes, the best team structure probably changes too.
That's the insight. So the frontier is topology optimization. The structure of the collaboration itself becomes a target for optimization.
How do they do that?
One way is to represent the workflow as a code graph, basically a program. Then they use methods like reinforcement learning or Monte Carlo tree search to find the optimal program flow for a given task. Systems like AutoFlow are all about this.
And the other approach.
The other is optimizing the communication graph topologies. So the search space isn't the workflow, it's the connections between the agents, who talks to whom and when.
It's like optimizing the org chart of our agent startup.
It is. And the most advanced systems, like Dynadswarm, realize that you need different org charts for different tasks. So they optimize a whole portfolio of structures and pick the best one for each specific problem.
And the absolute cutting edge, the ultimate goal, is what they call unified optimization.
Yes, this is the recognition that an agent's role, defined by its prompt, and the team's structure, its topology, are deeply interdependent. You can't perfect one without the other, so you have to optimize both at the same time.
So if we pull all the way back and look at the whole picture, what does this move towards lifelong self-improving agents really mean for the future?
I think the big takeaway is that AI is moving beyond being a static tool. It's becoming resilient. It's constantly monitoring itself, adapting, and refining its own architecture in this endless loop. This allows for really powerful, sustainable applications.
Like what are the big visions here?
I mean, we're talking about self-evolving agent ecosystems that could autonomously generate scientific hypotheses and then design the experiments to test them, or co-evolving software development pipelines that adapt as new tools come out.
It changes agents from just being executors into being these indispensable learning participants in whatever system they're in.
It does. But this brings us to the final, really critical point from the research. The core challenge of these systems is shifting away from just finding an optimal solution. The real challenge is defining what optimality even means in these dynamic, multi-agent worlds.
Right. When you have to balance raw accuracy against, say, how much it costs to run, or how you weigh the pressure to evolve against that absolute first law, endure.
Exactly. When you have an autonomous system that can rewrite its own rules, its own prompts, memory, and even its own team structure, what quantifiable standards should guide its evolution, especially when those goals might be in conflict? That is the profound and, frankly, unsolved question we're all going to have to grapple with as this technology moves forward.